talk about welding, and I probably cannot finish the whole thing. Next week we will continue to work on the welding part. So for this chapter, what we mainly focus on would be the welding material itself. We don't care about other components anymore. So for this chapter, we care about the welding. So welding is one way to combine multiple materials together without screw, bolts. Welding is one way to glue them together. However, if you weld the geometry in an inappropriate way, maybe when the component is carrying some loads, some area inside the welding material carries more loads, so you may have failure. Okay. So if we are focusing on this particular material, if I have one external load coming from the side going down, the welding material is gonna carry the external loads, and at the interface there will be some shearing force if the external force is going down. Okay, and are you sure everywhere inside the material is going to evenly share the pain, the stress? Maybe not. So the one key information about this chapter is that maybe some area carries more loads than other area. Okay? So now we this is about welding symbol, but I'm not going to talk too much. I just want to tell you about how to do calculations. So this is for engineering drawings. If you are making drawings for welding procedure, then you may need to know about these. But in the lecture, I'm focusing on stress analysis and failure. So mostly we are dealing with the triangular shape or this kind. So it's so-called the butt joint. So when you have two metal plates getting close to each other, you use welding technique to melt some material at the edge of both metal plates, and also you put some extra material right at this gap. So you usually have this particular shape. It looks like a triangle because some area of the original plate was melted, and at the end you end up with this geometry. And we usually assume, you have to figure out what's the effective stress area. For this particular case, if you are pulling the plates from both sides, then the effective stress area would be the cross section, the rectangular cross section. Over here, we just simplify the problem. We don't focus on the extra material on the top or the bottom. Sometimes you have some extra materials. You can use any tools to, you can like use a grinder to remove the extra material, that's fine. So for calculation, we don't consider the extra materials. We focus on the cross-section. Over here, the cross-section is H times L. That's why the stress will be the force over HL. That simple. Okay, for this particular welding joint, it's very simple. For shearing, similarly, if you have shearing forces that is lying along the geometry, the cross-section, then the effective area, the stress area, is still H times L. So for this particular case, the shearing stress equals to F over H times L. Now, for many cases, you will be feeling the corner of two materials. Sometimes they are multiple plates stacked together, or sometimes they are plates with 90-degree difference, such as 90-degree, it doesn't show here, like an L shape. So either it's multiple layers of horizontal plates, or one horizontal, the other one straight, forming an L shape. You are welding right at the corner, forming a triangular cross-section. What's happening is, in this particular case, when you observe its geometry, you usually see the width, AB, or width, BC. But in reality, the material has a narrower neck right at B and D, right here. So we call this throat, like your neck. We call this throat. So the stress area needs to be computed by the width of the throat, not the width right here, AB or BC. Okay? So here it's making a cut right at BD, and then try to show you the force inside the welding material. So there will be normal force and shearing force inside. So over here is trying to use the force balance to let you know how much shear force can be found and how much normal force can be found in this particular case. So by if you do let's see, where's the theta? Let me make drawings. So right here, okay, and this is supposed to be, usually it's 45 degree. Here is 45 degree. Then it's the analysis along any direction. So if you are focusing on this direction, at particular theta direction, in that case, you have a external force on the right hand side, and if you are trying to figure out the shearing force right here and the normal force right at the interface. So if I want to balance it, I will study at along the same angle. In this case, this is theta, so this is theta. So if you get the components, you will have this component, which is F sine theta, and this component will be F cosine theta. So by balance of force, F normal equals to F times cosine theta. And the shearing force along a particular angle equals to F times sine theta. Okay, so that's how you, if you want to compute the thickness right here by geometry, okay, right there. That's just simple triangular calculation. So once you have it computes the thickness. I don't want to spend too much time on this. So once you have the shear force and the normal force, you can then compute the cross-section area by geometry. Then you will get the shearing force and the shearing stress and the normal stress at the throat. So you can then use von Mises stress at this particular angle to figure out what's the equivalent stress. Okay, so we have learned this is an equation for von Mises stress for plane stress problems. Yes, for plane stress problems, right? Von Mises stress. Okay, so this is for you to know. You can figure out the stress condition at any particular angle. Right here, it's so over here, the textbook already did some calculation. The largest von Mises stress happens at a specific angle, 62.5. And the largest shearing stress happens at 67.5. So these equations, normal stress, shearing stress, and von Mises stress, you can see they end up with equations in theta. F is the same, H and L are the same, only difference is theta. So at different angle, you can do different analysis. You can compute their amplitude. And the textbook already did the calculation for us and realized the maximum value of these are not happening right at the 45 degree. Okay, so they occur at different degrees. Okay. So you can even make drawings, but in reality, there are researchers that has done experiments and realize in reality it's quite complex. Okay. So anyway, that's for you to know inside the welding material, if you are dealing with this triangular cross-section, even you can derive equations in at different angles, but experimental results are different. So over here, you can take a look at, this is basically the geometry, right? The geometry. So it's trying to let you know, here is the stress, and here's the stress. The dark, the solid line is the normal stress, and the dashed line is the shearing stress. So over here, right at this area, right at the bottom, it has a very strong normal stress and certain amount of shearing. And the shearing stress changes its sign. And for the bottom right here, it's being pulled up, but here is being pushed down. So it's actually quite complex. Okay. So because it's too complex, so usually we for extra analysis, we just focus on the 45 degree. So 0.7 is the square root of 2, right? So it's right at the 45 degree. Okay, it's a easier way, because if you focus on, if you take a look at the welding material, right at the 45 degree, it has the shortest distance. So right at the throat, it has the smallest cross-section area. If you take a look at here, it has a longer width. So here should be the shortest width. So smallest area. Smallest area implies larger stress. So for simpler estimation of the stress, we usually study the stress at the 45 degree. So that's why your cross-section area is right at the 45 degree. So here is your, which one is H? Okay. So this is your welding material, right? So here is H and here is L. So we are studying right at the 45 degree. So what's the length of it? So it's gonna be h over square root of 2, right? So square root of 2 is 1.4 something, and 1 over square root of 2 is 0.7 something h. That's why if you study the 45 degree, the cross section looks like this. Okay. So we only study the stress area right at the 45 degree. So the stress is gonna be your force over a smaller area than the regular area that we computed. Okay, so the stress is actually larger than how we expected. Okay. So right here, from here you can see the geometry of the welding material really matters, because it really depends on the relationship between the force and the geometry, the layout of the welding material. You really need to study the situation and then started to do some force analysis to realize which position is carrying more loads. So this is one another geometry where you have symmetry from top to bottom. You can cut this system into half. Then for the upper part, you have F going right, you have half of 2F. So basically F going right. So for this particular welding material, the force that contributes to shearing will be F. And the effective stress area is gonna be the cross-section area right at the 45 degree. So 0.7 HL. Okay? That's how you compute the shear stress in the welding material. Now, this is a very, you can say, popular, very common problem to solve. So what's happening for this particular case is you have, so before I continue, I need to let you know what does the drawing mean. This means we have, maybe there's a material like a base, and you have a plate to be welded on the base. So treat this particular treat my cell phone as that particular triangular geometry. So it's like you are welding my cell phone to the board. So how are you going to lay out your welding material? In this particular drawing, what the drawing did was, you did some welding here and some welding here. And now you apply some force from top to down at the right edge of this cell phone. So we are going to figure out which position of the welding material is going to carry more loads. So if this external load is getting bigger and bigger, for the welding material, which point is going to fail first? So we need to figure out which point carries the most stress. So the failure is supposed to occur right at that point. So if this point is carrying the most load, then we need to do some design. For this particular worst case position, how much safety we have? How much more load we can carry? Is it over
this material's strength. Okay, so this is a very a typical problem. So for this typical problem, there are two kinds of shear stresses. One is the normal stress. So for the external force right here going down, everywhere inside the welding material is going to distribute. It will be evenly share the shearing force, shearing stress caused by this external force. So the entire area here and here would be contributing for the normal shear force. So right here you can see there's a tau prime. What tau prime means is everywhere inside this welding material there are some shearing stress going down due to the external force. Okay? So then how about tau double prime? Tau double prime is the shearing force due to the moment. Because when we apply this force, it's not passing through the geometrical center of this welding material. So for the force analysis of welding material, now you need to figure out one thing. If you have certain welding materials like this, let's say you weld the geometry in this way, and this is here's a plate, and if you have some external force right here, so now this external force is going to rotate this plate. So there will be a center for rotation. So the center for rotation is most likely going to be somewhere here, okay? Because that's the geometrical center of the layout of your welding material. And if one day you change, for another case, you weld this plate in a different layout. So if I change the color, just to show you how they are going to be different. For case 2, if I only weld the top and bottom, not the left hand side, then the rotation center will be right here. Okay, so from here you can tell, you can kind of see, okay, due to the design of your welding layout, the rotational center is different. So the way you compute the transverse shear stress will be based on a different center of the geometry. So for the blue case, if this is this is the center 1, then the stress at any particular position is going to be normal to this radial direction. So this is going to be the stress direction of this particular point if this is the center of the geometry. But for the red case, if I'm studying the same position, but now I have a different geometrical center, so the shear stress is gonna be perpendicular to this radial line. So from here you can already see direction-wise the shear stress that is having clockwise or counterclockwise effect, the rotational effect is going to be based on the center of the geometry. So now, it's a very unique way to study, very unique chapter. For the welding chapter, the geometry of the welding material really matters. Okay, now let's continue to take a look at how those could be calculated. Here is one particular example of the welding layout. I probably cannot finish the whole thing, but you can see textbook specifically choose one vertical welding material on the left and the other one, a horizontal one on the top, and they are having different width. The left one has T1 width and the horizontal one has T2 width. So their width is different, just to show you how the difference of the width matters. So in order to find the center of the geometry, you first need to find the center of each welding part. So G1 is the center of this rectangular geometry, and G2 is the other one. So overall, the center of both will lying on the connection of these two, but we don't know where it is yet. We need to do some calculation to figure out where is G, the center of the overall geometry. Right here, what you need to do is to compute the throat area. So over here, we are studying the throat right at the 45 degree. So the throat is always 0.7 times h. Okay, and then here the length of the welding material for the left one is D. The length of the top one is B. So the total area A equals to T1 times D plus T2 times B. So T1 is actually 0.7 H1, T2 is 0.7 H2. Okay? Now, we need to compute I. So I is the area moment of inertia, because when we do this part, tau double prime, we need J. It's a shearing stress along the polar coordinate. So it's going to be J. But in order to compute J, you need to compute Ix and Iy first. J equals to Ix plus Iy. Okay, so how do you compute Ix and Iy? Based on, from usually in the back of the book, it's depends on which direction you're talking about. So for we are focusing on the left hand side first. This one here is x. So along Ix is gonna be T times Q of D over 12. But if you are talking about Iy, then it's D times Q of T1 over 12. So once you have Ix and Iy, sum them up, you have J. So that's the J of this particular area. Similarly, you can compute the J for the second area. So what's next would be finding the finding position of G. So what's happening is you can imagine that is the center of gravity. And you can treat G1 and G2 as the center of gravity of two different pieces of materials. And you can treat them as materials with the same density, but the area represents their weight. When the area is larger, it's like the volume is larger, so it's heavier. And it's like you are trying to find where is the balance, where is the center. So these two mass will balance for particular G. So that's how you can compute for the position of the overall center. So right here is treating, this is basically balance of moment. Why? It's using this particular coordinate system as 0. So if this is the support point, then treating these two are mass going down, and this is like a supporting force going up. So these three are having a balance of moment. So if you treat this one as the center, so the mass of this part is having a clockwise moment, so it's gonna be x1 times the area. Because area now is proportional to treated as weight. So the area right here times x1. This is like having a clockwise moment. So A2 times x2 both also has a clockwise moment. But A times x bar is the moment, counterclockwise moment due to the support, eddy support. So that's how you can compute for x1, x bar. Similarly, you're going to do the same thing for y direction. So this is more weird, because the way we draw this, we are treating everything as something with a mass. And it's like the gravity is going down. Then you can imagine, okay, you are supporting this point G with a reaction force going up. But for y, you have to treat the whole coordinate system in a different way. It's like the center, the gravity goes to left. If you do that, then y1 is 0 actually. So it's like the mass of this part goes down that way, and you have a support goes up this way. So you need to observe this balance in a 90-degree fashion. Okay, so once you are done with those, you have the position of this G in the position of x bar and y bar. Next, I think I will continue next time. Overall, you will be using a theorem that we didn't talk too much in this course, but you definitely have learned in the past. Okay, it's called the parallel axis theorem. So if you are interested, you can Go figure out, go review parallel axis theorem when you go back. Next time I will use it. This probably is the very few times that we use the theorem in this book. Okay, so before, at the very beginning of the course, if I tell you, oh, okay, we're going to use parallel axis theorem for the area moment of inertia in welding, you probably won't understand why. But now, because the area moment of inertia J lies on the center of gravity, center of the area. But now we are treating the whole thing as the complete area for carrying the shearing stress. So we need to compute the overall area moment of inertia for the entire geometry. That's why we need to study the area moment of inertia right at G point. That's why we need the parallel axis theorem. I will do that next time. Okay, so we will stop here. Make sure you do the attendance check. I will see you next Tuesday. And supposedly I will be finishing the welding introduction next time. Okay, that's it.